going to give a brief idea about what that robotics means, what kind of elements in that particular robotics, and then we'll discuss about sensors, and then we'll go for the mathematical modeling. But today we are only concentrating on only stuff that is what does that sensor means and how to use that sensor in robotics and what is the role of the sensors. So basically, when we look at initial stage of the robotics, you can just look at it. So this is nothing but in a somewhere starting point of the robotic system. It is going to evolve like in a human robot. This is the humanoids. Okay, and this humanoids need to be at developed because it has to embed that artificial intelligence. It should work like in a human being. That is what it is expected in the near future. So for that purpose, so many changes have happened. Basically, it has changed its way of mechanism, how it travels from one place to another place, and size of the mechanism, and so many other stuffs. And along with that, a different type of mechanism, then way of sensing also, sensing its environment. Like they may be measuring the temperature, maybe measuring the different angles, vibration, vision, so many stuffs. But these changes are still going to happen, and we are going to learn what are the changes has happened till the date, and what is the way we can look at robotic sensors and how it is to be done. Along with that, people have also developed a vision system. They have developed their mathematical models. They have worked on its own intelligence type of stuffs, like what it is called artificial intelligence, machine learning, vision, so many stuffs. So this is nothing but in a typical progress of the robotics. Somewhere this type of a structure was in somewhere 1960 or something, and this is nothing but in a current state of robotic system. This you can just go to the Boston lab or any lab online. There you can find how intelligent robots they have into intelligent robot project they are working on it, and they are developed most of this artificial intelligence based robotic systems. So today we are going to discuss about what it is and what is the means by robotics, why it is, and how the robotics we can learn and how we can create robots for so many other applications like any industrial application will be there, maybe medical health or any others. And then we are going to discuss about basic elements of the robotics. Then we'll more concentrate on the robotic sensors. Okay, because that is what the units I need to cover it. One is robotic sensor and another is in mathematical model. And then we'll have some review and question answers. So basically, I'm going to concentrate on the two stuffs. One is sensors. We are going to learn about what is meant by transducer, what is meant by sensors. I may be going in not directly to the robotics, but we are going to discuss about sensors. What is the basic principle of it, and how this sensors, what is the typical content of the sensor? Content means what are the different elements in the sensor systems, and different types of sensors, based on the basic principle like reliability is there, piezo is there, then strain gauge, load cell, touch sensor, force sensor, torque sensor, so many sensors are there. And after doing this entire, maybe this is taking somewhere 5 to 6 hours of period, and after 6 hours, we are concentrating on what way we can create a model of the entire robot. Means we need to represent that particular robot in terms of a mathematical equation. What is the way we can represent that particular robot in matrix, maybe and differential equations and kind of things. And then when we want to create a virtual robot and virtual environment, okay, and that robot we want to see how it performs on computer itself. We are not going to physically build the robot, but in modeling we build the robot and put on computer, and how that big robot behaves. If I apply a certain control system, how it behaves, All these steps to predict the behavior of the robot, whichever we are going to develop, is basically based on modeling of that particular robot. Okay. In that modeling, we may be learning some basic fundamentals of transformation, maybe a composite, homogeneous type of transformation, DH parameter. DH parameter is David Hartenberg. This is a scientist who represented how can I model the robot? Because if you are going to model any kind of a system, we need if I want to represent a single point into our any coordinate system, I need 6 degrees of freedom. But an DH, that is David Hartenberg, has represented this in terms of only 4 parameters instead of 6 parameters. And that will ultimately reduce the number of equations. If I want to represent a robot with 100 such points, and I'm using parameters, means 6 equations for a single point, means I have to solve 600 equations. Okay, that is what basically objective of DH parameters. And if I'm representing with only using DH parameters, I have to have I can do it within 400 different equations, and that is what we are going to learn it. And this DH parameters will help us to determine its position, its relative position between the elements or links and kind of things. And then when it is that robot in the motion, it creates an emotion. That motion is typically represented in terms of derivatives, that is velocity, acceleration, or kind of stuff. And for that purpose, we may be using a Jacobian type of transformation. Jacobian is nothing but taking a derivative of particular function with different variables, like a partial differential equation is nothing but a base for it. We'll discuss that also. Okay. So first of all, we'll discuss about what is the different content of the robot. If I look out the robot like this, okay, behind this robot, so many things are working. Basic thing working its mechanism. Okay, so that is a mechanical system. That mechanical system may have different links, may have joints, then actuators, sensors, so many stuffs are there. Okay, that is what in a mechanical system. And then after that, about that particular mechanism, you are putting in a kind of a cover, and that cover you are going to look at it. Okay, so when this mechanism has to move from one place to another place, or it has to traverse from one place to another place, it has to sense something. Sense means it has to sense what is the position of it. To know the position, I need to know the linkage, the relative position of the linkages. Okay, I means I have to know the what is its angle it has rotated, what is the current angle, what is its temperature, maybe what is its location, maybe using an XYZ coordinate sensors, I can sense the environment. And for that purpose, I need so many sensors. I may need a force sensor, I may need a motion sensor, position sensor, so many. Maybe sometimes I need a camera, I need a radar, I need a lidar, ultrasonic detection avoidance. All this stuff are nothing but sensors. Okay, that is what sensors. What that sensor does, sensor is going to sense that particular environment. Environment means if I want to sense the angle of rotation. So angle of rotation is nothing but my input to my particular sensor. And output will be in a conversion of that angle of rotation in terms of a voltage. And that is what it happens typically. Okay. That is the way it works. So when you are going to convert it, it will convert that particular signal in terms of voltage. Maybe this is converted into different ways, like a voltage or current. These are the two basic parameters. Why we need to do, if this is my input is my angle theta, this sensor will convert in terms of voltage. But this voltage or current, okay, These two parameters, how we are going to convert. What is the basic mechanical rotation is converted into voltage. And that is what it is possible through a different kind of a basic principles, like a resistance based principle. If you look at it into this. So in case of resistance means if you look into the potentiometer, how that potentiometer does, potentiometer will take theta as an input, output as an voltage. And that is what basically called as a sensor stuff. Once I got this voltage, why need to convert into the voltage? Because our microcontroller understand the language of the voltages or current. Okay, and that's what we need to convert whatever it is happening in this particular mechanical system, that should be understood by microcontroller, and based on that it has to take a certain decision. And that is the reason we need to communicate what is happening in the mechanism to the microcontroller by converting the information, mechanical information or thermal information, maybe an light information, in terms of a typically voltage information. And that voltage information will be treated as an input to microcontroller. And then microcontroller have its own memory, it has its own programming, it has its own logic or something. And that logic will now take in care. Just take an example. If you are going to design a robot and you want to see what is the temperature of the furnace or something, and if that temperature reaches to a certain level, okay, you want to take an action. Yes, I need to pick up something from that particular furnace. So what temperature sensor, you can mount a temperature sensor onto the robot. That temperature sensor means I'm going to have a temperature as an input to my system. That temperature sensor will convert into the voltage. This voltage goes to the microcontroller. Okay, this microcontroller will have its own logic. What kind of logic? If temperature, ultimately it is now represented as a voltage, is greater than 500 degrees Celsius, then actuate. This kind of a simple logic I told. So similarly, you can have multiple logical sets we can do it. And that is what it is written in terms of programming. And that program may be in a C++ program, maybe in a Python program, or maybe in a like program like an MIT App Inventor or any Scratch program. So many programs will be there. And then to actuate this, microcontroller has to generate a certain signal. And that signal will be generated. And this signal typically is in terms of 0 to 5 volt or something. Because this microcontroller, okay, works on either 0 to 5 volt or 0 to 12 volt. Okay, you want to drive in a motor here, maybe taking 230 volt as an input. Okay, that's what, and it needs more power, and this signal has a very less power. I need to amplify it. I need to convert that 0 to 5 volt to 0 to 230 volt or something, 0 to 12 volt, 0 to 24 volt, depends on the requirement of it. So what I have to do, I have to have a certain element, okay, and that is what it is called as an amplifier. Okay, what this amplifier does, it will take in a power from external power supply. Okay, and this external power supply will help to map 0 to 5 volt to maybe in a 0 to 12 volt, maybe 0 to 24 volt, maybe minus 12 to 12 volt, depends on what kind of an actuator I'm going to use, maybe 0 to 230 volt, like this. So this is what a conversion it does, and that is what also called as a mapping of it or something you can say it. Okay, and this conversion is converted voltage is given to the actuators. Okay? So then actuator may be in my BLDC motors, maybe a linear actuator, hydraulic actuator, or solenoid type of actuator, or so many type of actuators. And then actuator will now convert what are this voltage signal. okay, this voltage signal in terms of a kind of an emotion into my mechanical system. And that is what typically robotics does. So this is what on a basically very low level of a robotic concept, I will say. Along with this, there is one more stuff that is parallelly working. For this particular microcontroller, I need to do a programming. What kind of a program I can use it? I can use in a Python. Okay, that is one. I can use in a C++. I may be using in a Scratch, maybe using in a MATLAB. There are a bunch of the programming languages, R programming, and so many programming languages. You can find in a list of it. It's not a big deal. Okay, so any programming language works on such type of a logic only, because if this works, do this. If this is the value, then do this. That kind of a yes no kind of a decisions you can do it, and that is what the programming is. Okay, means I may have 10 sensors connected to the microcontroller. It is connected to port number 1, 2, 3, something. And based on that, port number 1 is if the port number signal is more than 2.5 volt, taken a decision to given a port number 5 output port 5, okay, as in something 0 to 12 volt or something. So this kind of programs or this kind of logic is implemented to the Python programming. Along with this Python programming, there is one more stuff that is going to happen. What is going to happen when you're sending that robot or any kind of a system into the environment? It is going to sense entire information, and that is what sensory system does. And this whole data you can collect, and you can collect the entire data. Entire data means, just take an example. I'm working on maybe a kind of a pumping station, water circulation pumping station, and I want to know performance of my pump. Means I may be measuring voltage current going into this, what is flow rate I'm going to do it, what is pressure, okay, or head it is going to measure. I'll mount all these sensors and I will connect, okay, I'll connect this to microcontroller, and this microcontroller is now collecting this information, and that information may be in terms of an Excel set with respect to time. I may be measuring voltage 1, voltage 2, voltage 3, current 1, 2, 3, maybe on a flow rate, maybe on a head, all these data. First second, second second, third second, like this, I'm going to collect this data. And this data, huge data I'm collecting. What is the reason to collect this data? Fundamentally, I want to know the performance of it, how it behaves. If my suction head is reduced, what is the performance of the pump? If suction head is increased, or if it is increased more, what is the performance of it? Or maybe outlet, some temperatures are something different, how it is behaves. Whole stuff I'm going to do it. If there is a certain fluctuation into the power supply, what is the performance of it? Whole data I will dump it onto my microcontroller. And this is a typically collected data. This data may be anything, maybe images will be there, maybe on a voltage signals, maybe on a current forces acting into the robotic system or something. And this data I want to relate to each other. Okay, and relate means I want to create a relation between the parameters. Why we need it? If I know the relation between the parameters, I can create a certain algorithm which will tell me the typical behavior of my system. And that is what it is called as a data analytics. And this data analytics is nothing but a nowadays very big chunk. That is, if I'm collecting more and more data, okay, and then it becomes then it becomes a big data analytics, okay, big data or something. I may be having such 10 robots collecting the data, doing their work, and then I will say it is a big data. Once I got this entire data, I know now I have done certain analysis, and that is what analytics it is called. And after analytics, I know the behavior pattern. I know if I'm going to increase this parameter, it is going to affect onto this. So based on that, I may be putting some mathematical equations, maybe an artificial or neural network model or something. And then I want to now take up an action onto this. Okay? Then I will apply a kind of an artificial intelligence or machine learning kind of an algorithms into this. And this is going to create this whole stuff is connected with an typically called as an HMIs, that is human machine interface, because this is an entire in a machine, and this is typically a tab or something. I may have on a computer screen as a human machine interface or something. And this human machine interface collecting the information, okay, from the sensors, and this also maybe converting, sorry, generating an instructions from human onto the robot also. Okay, so this is what typically works onto robotic system. Okay, and then what we are going to learn in next few lectures is we are going to learn about what is made by sensors. We are going to learn this much part. And we are also going to learn how to create a model of it, how to do an analysis of it. We are not going to learn what type of a microcontroller will be used or what is the structure of microcontroller should be there, what kind of an actuators or something. We are only concentrating in this course about these two stuff. One is on sensors, another is on mechanical systems or robots. We'll now look at what this mechatronics means. Okay, so is that clear what we are going to learn? Anyone can answer the question. If you have any questions, you can ask me the question. Am I audible, sir? Am I audible?
Yes, sir.
Yeah, I got confused whether yeah, I am audible or not. I would like to know, I would like to have a few questions at this point and then we'll move towards the next part. Yes, any?
Visible. Yeah.
Yeah. So we'll now move towards on the next part of it. How that sensor and how that modeling is to be done. We have seen different types of elements of the robot, which contains robotic system, then mechanical system, then sensory system, then microcontrollers, then drivers and sheets, actuators, then programming, data analytics, then artificial intelligence in machine learning, and human machine interfaces. That is what HMI. And then information will be collected from the sensors and instructions will be given to, or I can say it is in a commands to the actuators. Okay. So we are going to learn sensors and mechanical system, that is mathematical modeling of the data. If I look at what does that mechatronics means? Mechatronics means it is a typical integration of mechanical and electronic stuff. So in this, we are collecting the information from this particular environment, mechanical system, and through the sensors. Once I collect the information, means just take an example which are it is seen into the picture. It is in a typical dish type of an antenna. Okay, here it is in a potentiometer. Potentiometer, it is taking theta as an input to my potentiometer, and output will be in terms of voltage. Okay, so this theta as an input to my system and generating what are this middle element is typically a sensor which converts the value of the theta in terms of voltage, and that is what we call as a sensor. Once why we have to do, because our microcontroller or our data acquisition system understand voltages, not theta, angle or force or something. It understand only voltage signal. That's what we need to convert it. If I'm going into the China, if I'm or any other country where that typical Marathi or Hindi is not in a language, then in that case I need to use in a certain other language to communicate with them. That is the same concept is out here. So now sensor will collect the data and then here I got a voltage as a signal. And typically this voltage may vary with respect to time like anything. This voltage may be varying in this fashion, any voltage variation. Okay. But this conversion is also not typically possible by microcontroller to understand. And that's what, because in previous days, maybe 40, 50, 60 years back, these sensors are typically called as an analog type sensors. And now also we are using an analog sensors. In analog sensor, we are using a typically convert that information, whatever information you are collecting, in terms of a numbering system, that is what in a decimal numbering system. What does that decimal numbering means? It is taking 10 as a base for it. Okay, 10 base system means I have on a 1 bit of the information. This is 1 bit. I may be representing within a 2 bit of the information, just that. And I have a counter here, and maybe connected within a kind of a rotor or something like this. I mean, this is the knob I'm going to rotate about it. And this is going to convert 0 to 9 numbers. Okay, I may be switching. Once it is reaching to the 9, when it is again, it will come to the 0. And that is, then I'm going to switch. Here also, I have another number that is what? 0 to 9. This is my first bit of the information. This is my second bit of information. So 2-bit information. Okay, and this is what it is called as a decimal numbering system. Okay, I have how many steps into this? I have a 0 to 9 steps here, 0 to 9 steps here. Altogether, if I want to cover all this, how many number of steps I have to go? I have to go for 100 number of steps. How can I do it? I have 10 steps here. For each this number, I have 10 steps. 10 into 10, then it becomes 100 number of steps. Okay, that is what typically decimal numbering system works. But in case of a binary, instead of this 0 to 9, that is a 10 number of steps, 10 steps, there will be only 2 steps. Okay, 2 steps means I have either 0 or 1. Okay, I will now change this number of steps to 0 to 2, 0 and 1. And this is representing only 2 steps. Okay, and these 2 steps are represented in terms of binary numbers. This is what, either 0 or 1 something. Okay, so this is to be converted because microcontroller understand binary stuffs. The reason for this development, because previously there people are using measuring voltages using a multimeter or something, analog type of multimeters. Okay, in this analog type of multimeters, okay, so we can have a variation 0 to any variation, but in digital once. But when I want to get a better accuracy, I want to know the exact information. So for that purpose, that electronics is not much more sufficient to represent anything into the 0 to 9 steps because it needs so many registers, transistors, so many stops inside it. Okay, even binary also facing a lot many difficulties. So in that case, then people have thought it to have a new development that is binary system or 0 and 0 and logic. That is what it is called as a digital. So conversion of this decimal numbers or analog numbers, it is called as a typically analog number in terms of binary numbers or digital numbers. Okay, that is analog to converted into digital And that's what it is called as an ADC. This is the device which will convert decimal numbers into an analog numbers. And that is what in a logic you can find it onto your calculator also. Okay, you can just put up in a binary, binary, it will convert into 0 and 0 logic. That is what we can see. So once it receives this binary code, means this all the numbers will be 0, 1, 1, 0, 1 like this. Okay, this is a typical number. Now this can be quite easily understood by a microcontroller. And this microcontroller will have its own memory. And that may be put into logic. That memory is typically a RAM type of a memory. Some logic is kept. And based on this is the numbers, it will take up in some action based on what are the logic you have put it. And it will convert that into an again digital number. And this digital number is again 1 0 0 0 0 0 1 like this. The number of bits, what is the bit accuracy of it? Based on that, it will convert it to digital. But here there should be some device, because your actuator doesn't understand this particular language. Okay, it understands 0 to 9, or it understands decimal numbers. Okay, and it understands analog language also. Okay, these all are one and the same. So what I have to do ahead, I have to convert that digital numbers into an analog number using a certain device. So that is what digital to analog conversion, that's what DAC it is called. And this device is taking care of it. It contains some certain kind of registers, transistors or something. Okay. And then DAC is further connected to, then it is amplifying electronics. Why we need an amplifying electronics? Here, this sensor, just take an example. This is my theta is input. Here I am getting an output 0 to 5 volt. Okay, maybe I'm having a current is maybe 5 milliampere or something. And total power of the signal will be in a 25 milliwatt or something. Okay, not more than that. Okay. And this is converted into ADC, the same amount of power it is. But this microcontroller takes an input as an maybe 0 to 5 volt or maybe a 12 volt or something. This is also very having a 2 amperes current, not more than that current it will take. And it has not sufficient power, maybe hardly maybe a 0.5 watt power or something. It is this 0.5 watt power is not sufficient to drive this bigger motor. This motor may be a 0 to 12 volt or 0 to 24 volt or something, which needs maybe a kilowatt of power. Okay. So we need to convert here what are the signal coming into 0 to 5 volt with a 5 milliampere current to larger values, maybe 0 to 12 volt or maybe 0 to 2 ampere or something. This is what I need to convert, or I need to map it. So for that purpose, there isn't a kind of an electronic stuff it is called that is amplifying electronics. And from where that power is taken, it is taken typically from power supply. Sometimes we use a DC power supply or also AC power supplies. Okay. And this power supplies, that is operational amplifier or something. It supplies current and voltage to this. Okay. So this powers will convert given to the actuator, and then actuator will start actuating. So this is what typically happens in this typical mechatronics system. In this mechatronics system, okay, we'll now look at what does that sensor means. Okay, so we are going to look at the sensor part of it. And this sensor is if you look into any kind of a sensor, it has a capacity to sense something. Sense something means if I want to know how much it is hot or cold, it is called as a temperature as a parameter. If I want to know how much amount of displacement it has happened, then it is displacement or motion. I want to know the velocity. I want to know the image, what is light intensity or something. So this is typically called as a variable of the sensor. This is my input going to my sensor. Once I got this input, next steps, I want to convert what are this parameter in terms of a certain electrical signal. That is what it is called as a sensing mechanism. This sensing mechanism may be a simple potentiometer, anything. So I'm going to change the angle. That angle, amount of angle will be converted into amount of voltage. That is what a typically sensing mechanism. And that sensing mechanism is converts into electrical signal. So when we are going to deal with this particularly a sensing mechanism, I may be using a resistance change. I may be using a delta R change or something. I may be using a delta capacitance into this. I may be looking at uh, magnetic field. Okay. I may be looking at voltage change using a force that is piezo. Okay. I may be looking, so many basic principles will be used. And based on this basic principle, we need to set up a mechanism into the sensor, which will convert that particular variable, sense variable into an electrical signal. And that electrical signal, maybe in terms of it, maybe contains certain noise. Okay, what does that noise I will tell you? I know this is my with respect to time, temperature, I'm going to monitor. My temperature is, I know of the heater is 100 degrees Celsius. Okay. This 100 degrees Celsius temperature is sensed by this sensor. This mechanism has its own limitations. What kind of limitations? It may get interfere with a certain external signal, maybe a waves or maybe a temperature around it or so many stuffs. Okay, and that signal will be now with respect to time. This signal may be in a varying like this, not showing me 100 degree, but it is varying between maybe a 99 to 101. So what are this variation is called as a noise, which we don't want it. That's what it is called as a noise. Okay. So this noise will be there because of different aspects of an entire sensory system. One is due to the sensing mechanism itself. Another is what kind of an environment it is and kind of stuffs. Now I don't want this noise to be there to my signal. What I will do, I will put up in a certain filters into this. So that is what kind of filters I can buy. And these filters, okay, are this is called as a signal processing. That is filtering in it, amplification, so many things. If I'm using an amplification, why it is necessary amplification? If I'm using just take an example of thermocouple, okay, this thermocouple will have a sensing capacity of 0 to 500 degrees Celsius, okay, and it converts this maybe using a CBAC effect or something. It is converting that signal within a 0 to 50 millivolts only. Okay, for 0 degree, it is going to give me a 0, 500 degree, it is going to give me a 50 millivolt. Okay, now when we are converting that, this is very low signal as with reference to your microcontroller. Microcontroller can understand a signal within a 0 to 5 volt or 0 to 10 volt or something. Compared to this 0 to 5 volt or 0 to 10 volt, it is in millivolts. So obviously I need to amplify that. And that's what we need in amplifiers and sometimes in sensors also. So in case of thermocouples, we need an amplifier. In case of strain gauges, also we need an amplifier. And that is what amplification also may introduce kind of a certain noise into this. And this kind of noise is also major concern into this. Okay. So here to remove this noise, we need in a filters. Okay. And that whole stuff covers as in a signal processing unit. And once I got the signal processing unit, then I will now got this. to the data representation unit. In this data in representation, maybe I can record in terms of an Excel sheet or text sheet or something. I may transmit that data to some other Wi-Fi or something in it. I may display also. I can have a display unit, digital display or something. So this is what typically a sensor does the work. What we are going to do it, we are going to learn how much resistance change and how much temperature is going to change. That is what a sensory mechanism. Okay. हेलो हाँ अरे भी जरा काम आता है मैं बोल तो इसी लेक्चर में so you now understood what that sensor contains. Okay, now we'll look at a different aspects like okay. It needs any variables to sense, sensing mechanism, then electrical signal with noise, signal processing unit with amplifiers, then data representation, maybe any of this, and that is what it does. We'll now look at what that data acquisition system means. That is what that microcontroller does the work. Okay. So when we are going to have a sensing in it, then signal conditioning, we have seen it, then analog to digital converter. Okay, analog to digital converter. Already we had a discussion on it. Because here I'm getting a signal in terms of a decimal numbers. Okay, or I can say it is an analog signals, and that is to be converted into a digital signal. Okay, this digital signal are binary numbers, and that is what analog to digital converter will be used. So how it converts, how many number of bits are there, what is the speed at which it will convert, all these parameters will play a very important role, and that is what an ADC will be a major component into this. This ADC is connected to your microcontroller, then microcontroller will now take this information, pass on to your logical program. Logical program will analyze this. Based on that, there is a certain logic, and it will generate an output to the microcontroller. And this microcontroller will now convert that signal into analog signal, because here this whole stuff works in decimal numbering now. That is a binary systems. Okay, and this whole word works on decimal numbering or analog system, I can say. Okay, and then again I need to convert into analog signal, then power amplifiers or current amplifier, voltage amplifier, so many steps will be there, then actuator, and then it will work. So this is what in a typical sequence it happens, information flow sequence. Kind of. Hello? हाँ बोला. मी लेक्चर मध्ये मी नंतर बोलतो तुझ्याशी. Okay, so this whole stuff, that is analog to digital converter, then microcontroller, logical programming unit, then digital to analog converter, all these combines into a single unit, and that is what is called as a data acquisition and microcontroller. This also we are going to learn how it is connected to the sensor. How can I plan my sensor should sense it more accurately, and that is what depends on data acquisition system. Okay, already we have gone through these slides. That's variable to sense, sensor for variable to measure, then electrical conversion, and signal processing and digital indicators. Okay, so now we look at a difference between analog systems and digital systems. In analog system, a variation will be anything. Okay, will be means anything, means I want to sense the potentiometer. Okay, I'm going to convert into 0 to 360 degree. I may sense 181.22345 something, any number. That is what it is called as an analog system. But in digital system, what it happens, it sends in certain number of steps only. Here also we are using in a steps, but in one single beat we have in a 10 steps into this analog system. But in digital system, we have only two steps in a single bit. So that's what, if I look into this, this is going to give me a more smooth variation as it is taking 10 steps into a single bits. Here I have on a two steps into single bit, it is going to convert into this staircase effect. Okay, so what does that means? If I say and my voltage is 0 0 level, it is like this. This is 0 0 0 1 1 0 1 1 1 0 0, like this. This is a three-bit system. So my if voltage is beyond certain value, it will shift it to the next value. Like this it works. And what this is typically a difference between analog systems and digital systems. And if I'm going to use this ADC and DAC in between my computer and my mechanical system or any other system, then it becomes a digital system. Otherwise, it is a 90% of the systems of whatever existing in nature are analog system. So it happens, there is a physical phenomena happening, it is generating a certain parametric value, transducer will take up an information, convert that into a voltage. This is a typically signal conditioning in it, which will maybe using in a use for amplification, maybe a voltage maybe filtration, so many things. Then there will be a data acquisition module. Then it is connected to a personal computer. Nowadays, this data acquisition in it is typically a Arduino board also will be used. Arduino board, Raspberry Pi, all this comes under the data acquisition unit. Okay. We'll now look at what is meant by a bit accuracy. How, if I connect a certain sensor, okay, how it convert that into the number of bits. Okay, so here if I look into the two-bit system means I have one bit here. This is my one bit, and this is my second bit. So it starts with 0 0 0 1 1 0 1 1, and so I will get only 4 steps into this. Okay, so these 4 steps means 0 to, yeah, if I want to sense a voltage up to 0 to 5 volt, means maximum voltage sense can be a possible only 5 volt. Okay, I want to know if I want to say a 0 0 voltage means my voltage value will be 0. Here it is, I can write it in 0 volt. Okay, and then if I want to means this is what an analog signal, red line indicates analog signal. Okay, and here at this particular location is 1.25 volt. Okay, is my 0 1 stage. Then 1.25 to 2.5 volt, and then 3.5 3.75. This is my 3.75, and this is 5 volt or something. Okay, so if my signal is beyond certain value, beyond 3.75, it will sense into 1 1. And if it is beyond 2.5, it will sense into 1 0. 1.5 will sense into 1 0 1. So this is what it is represented in terms of a 2-bit accurate system, 2-bit accuracy. If I want to get a more accurate sensing, means what that particular stuff it is going to tell is it can sense either 0 volt or 1.25 volt. If voltage between the 0.0 to 1.25, it can't sense, it will sense as a 0 0 volt. And that is what a limitation of the digital system. So if I want to come out of this limitation, I can go on adding some more bits. Okay, here it is in a 2-bit system. I'll get a number of steps into this is 4. If it is a 3-bit system, I'll get number of steps into 8s. So here it is in a 0, then 0, 1, 1, 0, 1, 1, 1, 0, 0. Like this, I can have an 8 bits. So I can have on a 0 volt here. I can have on a 0.625, then 1.25, then like this up to here it is on a 5 volt or something. Okay. So I will get now, if increasing only one single bit, I have improved the accuracy. Previously in 2 bit, I'm getting an accuracy of measurement is 1.25. But here I'm getting an accuracy of 0.62. Okay? 0.62 means I can't sense the voltage between zero point 0 to 0.62, but I can sense 0.62 and beyond it. So that is what it's called as a resolution. This is what my resolution of my system. Now I want to improve one more bit. What way I can do it? I can go for increase the bit. Okay, 2 raised to 4. Altogether, how many number of steps? There were going to 16 number of steps. So 0 to 5 volt, how many steps? I'm going to for 16 steps. I can get an accuracy of 0.3125. Means here it is in 0.3125. Then here it is in a 0.625 something. Like this, I will get here up to 5 volt or something. So here now my resolution is how much? 0.3125. So that is what, if I go on increasing, okay, increasing number of bits, I can get in a better and better accuracy. Now we'll see it. If I connect this to particular sensor, how it works. Okay. So I have just taken an example of typical water level sensor tank. In this tank, I have on a level 0 to 40 volt. Okay, and I'm using a 10 bit output. Okay, this is my level sensor or level transmitter, I can say. So it is going to sense that in terms of a head or something and convert into the voltage. This is whole is analog stuff, and I want to convert into digital. How that digital will convert? So into 10 bit system, how many number of steps will be there? 2 raised to 10, it becomes 1024 number of steps. Okay. So this 1024 number of steps means at 00 bit, here it is all the bits are 0, I'll get in a 0 voltage. And if my all bits are 0 level, and here all the bits are on, I will get in a 40 feet of the distance. That is 40 feet of height in the water tank. I want to know how much accuracy it can sense. If I change only one single bit, means I have on a 40 number of steps, 40 foot divided by 1024 will give me a 0.03901 foot as a minimum resolution. This is my resolution I can get. Means for this particular step, I'll get a 0.039. Then next step, I'll get 0.078. Or likewise, I can go for 40 bit. So this is way, if you want to have a better and better accuracy, you'll get a more and more accurate or resolved kind of sensing and in this case. Okay. So another one example is both the things, actuator and sensor, that today I'm going to give a lecture to you. What are the sound generated by my mouth will be converted into air pressure. Okay, so that is what an air pressure will now vary like this or something. That will hit to microphone, and that microphone is now converting what are the air pressure or hitting onto the microphone will be converted into voltage signal. Here I will get a voltage signal. Okay, and this voltage is further converted into digital signal. So continuously it is happening. Whatever I am going to talk is converted into digital signal. And that digital signal, okay, is further given to the microcontroller. And based on this microcontroller, again it convert that microphone with a more amplified manner. that in terms of digital signal, and then it is going to DAC and goes to speaker. So this is what it converts. Okay, so you can just look at this animation, you will come to know. This is sound wave pressure. It is hitting to my microphone, converted into a voltage signal. This is my voltage signal, which is typically analog. And that analog signal is converted into digital signal. Okay, then here my DSP, that is digital signal processing unit, will be taking memory and again converting into again digital signal. Then it is converting into analog signal and given to the speaker. So that is what an ADC and DAC application inside a single unit. You can see it here. So we now have what kind of phenomena, what kind of stuff, or what kind of an environment or parameters you want to sense when you're doing robotics. In this case, we may be using a different stimuluses. Stimuluses means different principles of sensors, like an acoustic principle. Acoustic principle means it is either amplitude, either phase, or polarization, or frequency, so many things will be there. Okay, spectrum, wave, velocity, all will be converted into electrical signal. And that is what an acoustic stimulus means. It is a sound conversion, sound to voltage converter. Then there will be a certain biological or chemical like in a fluid concentration, pH values, maybe a biological, any kind of an activity, reactions will be converted in terms of an again voltage. And we are maybe using a certain biological principles for this. Electrical, we may be sensing charge, voltage, current, electric field, amplitude, phase, polarization, conductivity, permittivity, all this comes under the electrical phenomena. In magnetic, what is going to sense? We may be sensing a magnetic field, amplitude, phase, polarization, flux, permeability, and so many stuffs. Then optical sensing, we may be sensing an intensity of the light, refractive index, reflectivity, absorption, all this. In thermal, we are sensing a temperature, flux, heat, specific heat, thermal conductivity, and so many things. And in mechanical, we are sensing position, velocity, acceleration, force, stress, strain, pressure, torque, so many other. So to sense these parameters, we are all the time using a certain basic principle behind conversion of this particular parameter into electrical signal. And that is what we are transforming that information in terms of an electrical. That's what also it is called as a transducer. Okay. We'll now look at resistance-based measurement. That is what potentiometer. Okay, this is very handy and very interesting stuff. Okay, so here you can just look at here. There will be three wires. Okay, this wire is connected. You can test this pot using. You can at home also. You can pick up any pot, apply a voltage. Here I will apply a negative side of the voltage, and here it is a positive side. Here I will apply a 5 volt, here at a 0 volt. And this is my output wire, middle. Okay. So as I'm going to rotate, if my wiper or my water knob position is 0 here, so voltage is sensed between, it is going to pass through the resistance. Means what is going to happen if I consider, I will just straight out here. So this is what an entire resistance. Here my voltage is 0 volt, and here it is in a 5 volt. It is in a potential difference. Okay, I'm putting one wire here. What are the voltage across these two terminals is a 5 volt. That is my base or supply voltage, I can say. And if I want to sense the voltage between this point and this point, is called as based on position of this knob. Similarly, here also the resistance of this and resistance of this. So that how can I calculate? I can have total resistance from this point to this point, and what are the resistance it is going to cover between this. I can take up in a ratio and I can get the potential voltage output. This is what basically we mostly use for rotation angle sensing, position sensing purposes. It cannot be used for a very high speed because it is based on a kind of frictions. Okay, it rotates. It slides on this particular wiper slides on this particular resistance. Okay, so as we are going to have a faster motion, it cannot sense it more accurately, and because there is a physical touch, there is a friction in between. And there is also, if I'm using a very high voltage or something, there is a possibility of spark or something. So for that purpose, it is only used for mostly in static type of measurement or very low operation measurement, low speed or low motion operations. This resistance based measurement, that is a potentiometer will be used. Okay. So to determine how much voltage output, this is my voltage in. What is the voltage in is 5 volt. Here it is the voltage out. Okay, which is determined by this typical formula. So we'll now have there will be two types of potentiometer. One is rotary type of potentiometer, and another is linear type of potentiometer. Both cases, the formulas will be the same. Okay, what are the change in the resistance? What typically it is going to happen? Initially, input parameter is my theta angle. That theta is change in the resistance, and this change in the resistance will be converted into change in the voltage. This is what the flow of the information is going to happen, and so theta to this delta r. This is what the relation you can use. That is R AB divided by R. Okay, and this, if I multiply with supply voltage, I'll get Vs into R AB divided by R like this. Okay, that is what conversion will happen. And same is there the case with this linear potential. We'll now have one simple example. Okay, for this case, we have a potentiometer having a range of rotation that it can start rotating from 0 degree to 350 degree. Okay, for 0 degree I will get a 0 voltage, and for 350 degree I will get a 10 volt. Okay, and I want to know, okay, if this pot is set at 82 degree, what will be the output voltage? Okay, output. That is what a simple thing. You can just look at a typical picture of this. This is my motor. This is arm. This is voltage, that is a ground. This is 10 volt, and this is output voltage. If this arm is set at 82 degree from 0 position, okay, what will be the output in this whole output from the potentiometer? How can I do it? I want to know unit change first. I will convert that into unit change, and based on that unit change, I will multiply that unit change. I will multiply with an 82 degree, and that unit change is typically called as a transfer function also. Okay, we'll now look at how that transfer function of that particular pot. In pot, what is going to happen? I'm going to have this pot. This is pot. I am going to have a theta as an input, output as a voltage. Okay, so transfer function of this pot is my output is voltage and input is my theta. Okay, so this is what a typical transfer function, output divided by input. How much voltage transfer function it is having? 10 volt as an output. For what angle? That is a 350 degree. So I can get this ratio. This ratio is called as a unit change, or also it is called as a gain of that particular sensor, or also called as a transfer function. Okay, so there are different names for it. You can use any name. There is no issue in it at all. So unit change means per degree, how much voltage will change. Okay. So per degree, because degree is in down, that is in uh, denominator. So obviously unit change tells me a per degree change, change of voltage. Okay, so that is what it happens. Okay, so here once I know this, I can multiply with an 82-degree. I can get an voltage output 2.3534 volt. So that is what the way this potentiometer works. Okay, you can use this numerical for your simple calculations. Okay, so now we'll have one more example. Okay. One more example because why I'm going to take in one more example, there is a specific reason for it. Okay. So we have a 10 kilo ohm pot. Kilo ohm is nothing but a my resistance. Okay. Previous example, we not thought of to use any resistance as a conversion, but directly we know that 0 to 350-degree and 0 to 10 volt. But here that resistance is also taken into account. Okay, 10 kilo ohm pot is used as an position sensor. Okay, when wiper is at a middle and its range at this particular middle point. Okay, loading error will be like this. Means interface circuit represents this wiper is connected with an interface circuits that may be an operational amplifier or any other device. So I can have an infinite resistance, one option. Another option, I can have a resistance of 100 ohm. There will be two options. Okay. So when we are going to, why there will be two options? Because when it is going to sense it, the voltage will flow through this. And when it is flowing, that resistance plays in a very important. Okay. In ideal situation where interface circuit resistance is so high that there is no current flows through the pot wires. Okay. Pot will behave like a 5 kilo ohm resistors in series. Okay. And that is what it gives me 5 or something, and it gives me 5 volt or something. Okay. Well, as we would expect that pot voltage is exactly the half of the what are the supply voltage. If your circuit having a certain limited resistance or there is no loading, means there is no loading error into this, then if I consider that resistance, what will happen? Okay. See, in this case, here I consider as an 100 ohm as a resistance. Okay. Now, can I convert this diagram into this? This is 5 kilo ohm, this is 5 kilo ohm, and here it is 100 kilo ohm. Okay. Now, here 5 kilo ohm and this 100 kilo ohm, this both will convert. Okay. These are two parallel resistors, will be 4.76. That is effective resistance. I got it. Okay, here 4.76, here it is in a 5, and I am having a voltage 0 to 10 volt. So this is going to give me a 4.88 volt. If this resistance was infinite, this voltage is will be 5 volt. So how much error will be there? Error will be typically 5 minus 4.88. It will give me a 0.12 volt as an error in the measurement. So whenever we are using any kind of a device, make sure that all the parameters are ideally fit into this. If it is not there, kindly identify what is the reason behind it. Okay, and then you take up on a proper calculations or something. Once I got this, I can have an actual pot voltage should be in a 4.88, but when it should be in a 5 volt. Okay, loading error will be 0.12 volt, and that is what you can take up care of it. Okay, and you can put this into a simple calculations, and you can go on doing all other calculations also. There is one more similar example. Okay, for potentiometer, the resistive element of wire wound pot is made of a 10-inch. Okay, 10 inch is the length of it. Okay. Wire wound means that typically I can show you here. This is my pipe, okay, and then wire is bounded onto this like this, okay, wire wound, and there is one wire here and second wire here. This is maybe a ground or maybe a voltage or something, and I'm going to use a slider, okay. And how many number of loops are there? Altogether, I've gotten a 200 number of loops of coils. 200 number of loops of coil. And the range of what is 350. Means if I have this is my slider, okay. I have one wire, then second wire, third, like this, okay. I assume that pitch of this loop is the same everywhere and it is not going to change. I assume that it is machine use means what are the looping is done using a machine and it does perfect, okay. But in actual practice, this doesn't happen, okay. And this is a total length of it is 10 inch, okay. Then I'm using in a pot here, okay. This is my pot, okay. And I want to know what is the accuracy of it. What is the accuracy I can measure it? Means when that my slider is at this location, I want to know the signal and voltage. Here I will get in a V1, here I will get in a V2, and resolution is nothing but in a V2 minus V1 or something. And that is what I want to know it. So total 10 inches my distance, okay. And per inch, how many resistance is there? 100 ohm. So total resistance becomes 1 kilo ohm. 100 into 10, that's it. So 1 kilo ohm resistance is spreaded onto this 10 inch, okay, with a 200 number of turns, okay. Now 1000 ohm divided by 200 gives me a per turn. I'll get a change of the resistance here is my 5 ohm per turn, okay. That is what I got. This is nothing but a resolution in terms of a change in the resistance, okay. How much supply voltage, and based on that I can determine how much accuracy, or I can determine a percentage accuracy also. Change in the resistance is my 5, and total number of 100 is my limitation. Then I connected with a rotation, that is a resistance, total resistance. I can get a 0.5% accuracy, I can get it, okay. If wattage to be used as a position sensor, it would be useful to know that resolution in terms of degrees, not in terms of percentage of the total range. The smallest measurable change corresponds to one loop of resistance coil. Watt is divided into 200 watts, 350 divided by 200 watts. Therefore, my accuracy of measurement will be 1.75 degree. That is what the way you can determine accuracy in the potentiometers. So this is what typically potentiometers. Okay. If you have any questions, you can ask me now, and then we'll move towards the next part of it. Yeah. Yes, sir. Can you hear me?
Yes. Hello, sir.
Yeah. If the students have any kind of questions, they can ask.
Yes, sir. Students, if you have any doubt, you can ask. Yes. Anyone. हॅलो, काही डाऊट आहे का कुणाला? देशमुख सर,
हा बोला.
पुढे कंटिन्यू करायचं आहे का?
तुम्ही म्हणणार तर मी कंटिन्यू करतो, काहीच अडचण नाही. आपला
हां सर बोला.
किती 1 वाजले का?
हां 12:50 हां 1
अजून
वाजले.
किती वेळ आपल्याकडे किती वेळ आहे पण सध्या?
ॲक्चुअली 2 तास असं होतं ॲक्चुअली तसं काही हे नाही मला प्रॉब्लेम नाही.
नाही, अजून एक अर्धा पाऊण तास घेतले की होपफुली इट विल बी बेटर आय थिंक. ओके.
हो सर हो चालेल ना.
मुलांना काय अडचण नाही आहे ना?
हां सर तसं काही वाटत नाही कारण मी ग्रुपवर पण शेअर करतोय की काय डाऊट असेल तर इकडे मेसेज करा मी
ओके,
सांगून
ओके,
देतो.
ओके. एक 2च मिनिट मी ब्रेक घेतो आणि देन विल
हो
स्टार्ट.
सर हो चालेल.
Okay, soon we will start it again. Okay, we have discussed about how that resistance of potentiometer or uh, any that is converted into voltages, and how can we convert what are the input motion, maybe an angle, maybe a linear position in terms of voltage signal. Okay, we'll now look at what is meant by strain. Okay, strain is nothing but it cannot practically it cannot be measured. Okay, I will tell you why it is called and how we can do it. Okay, I will just go back to one slide. Okay, so in mechanical we measure on a stress and strain. Okay, but on stress and strain practically it is not possible to measure. But actually we measure in a force and deflection. Why I will tell you the reason for this. So basically, if I take a rod of this size, okay, I'm going to apply the force onto this. Okay, this is my area, and this is the length, and this is the force. And I want to know the behavior of it. What I can do it, I will now have on the table like a force and deflection plot, and I'm going to do this all experiments onto this. So when I'm going to do this, I will now plot this a two graph, one graph, force versus deflection. So in initial case, it is observed that my displacement and force, it is increasing like this, and then later on it will increase, and then it will fail into this. Okay. So this is for typical numbers, like what is my area and what is my length and all this. These are the geometric parameters. If I consider this as in a typical system, input is my force, output is my deflection. Okay. So how it is going to convert? There will be two steps into this. One is my geometry of my structure. If I increase the diameter, that curve will be something different. Length increase, curve will be something different. That is what in a geometry dependency. Another one is a material property. If I have an steel, I will have a different curve. I will have if I have aluminum, concrete, this is what. That is what in a material variation. In geometry, we are using here two parameters, that is the length and my area. Okay. So if you increase the length or area, so this is I will consider as an AGO. Then my another curve will have a parallelly it will run and it will fail like this. This is my area. If I increase one more area and then I will have an A3 as an curve. So I want to test it and I want to use this component in practical. Okay. In that case, I can't go for so many number of curves and store that entire data and do the analysis. Okay. Instead of that, what I need is I want to remove the dependency of the geometry. Okay, between this force and deflection. Okay, I want to remove the dependency. How can I do it? If I want to remove the dependency of the geometry, force is acting on the area. Okay, I will now, instead of area 100, maybe 200, maybe 500, maybe something else. Instead of that, I will consider as an unit area. How can I do it? I can now convert that force upon area as a geometrically independent parameter, and that is what it is called as stress. And now I can have stress on one axis, that is force area. And similarly, this deflection is again depend on the length. Okay, this is my length parameter. I'll divide this length and I will consider strain delta upon level something. This is a per unit length change, per unit length change. That is what we call as a strain. Okay, and this strain is further converted into force, depends on geometry and so many stuffs. And then I can get in only one single property material. This is for steel, I will get. This is for aluminum. This is my aluminum. This is for some high strength material, like I can have a diamond or something. So this is the reason why it is force and displacement or deflection, rather, I will say, is to be converted into stress and strain. But in actual practice, we are not able to measure stress because stress is per unit area, force on per unit area, which is it is next to impossible to measure. We can measure actually deflection. I can have on a certain sensor which will measure the deflection and then how much deflection was happening, what is my total length, and based on that I can quite convert it. And then I will say it is in a strain. Ultimately, we are using a strain. And then there is one rule we can observe into this is a typical rule. It is a this is a linear up to this point. This is my proportional limits. Okay, I can linear means it is showing this is my input to my system and this is my output from the system. The relation between these two input and output is a straight line, and that's what it is like. You can say it is linear up to this point. But beyond this point, this becomes a non. Okay. Beyond this point, it is a non-linear. So we are much more interested into this zone. We are not anywhere interested into this zone because that is what the strain you want to measure it. Okay. So we'll now come back to our strain measurement. Ultimately, we came to know what does that strain mean. Strain is nothing but a change in the deflection upon the length. Okay. So that is the basically a strain it is called. Strain, so if you look into the market, you will get a strain gauge. Okay. This strain gauge is typically a wire type or foil type or something. What is going to happen? This is my wire. Okay. Having a resistance R. Okay. And if I having a length L, okay, the total resistance is R. If this L is increased to somewhere delta L, the resistance also changes to R plus delta. This is what I want to take into consideration, and I want to now measure use this for measurement of the change in the length. Means amount of delta R change is directly related to delta L. Okay, so I can have a more length wire. I can get in a more sensing. Small length, I'll get in a less sensing. That is what it typically happens. So this is a typical sensor, okay, which has in a 2 points. One is resistance measured, these 2 points. Okay, if I pull it longer, if the length is increasing more, then I can say it is tension. If it is length is decreasing, then I will say it is a compression. Means resistance is decreasing. Means if I am going to apply the compression force, then L length will decrease, and ultimately it is going to change the reduce the resistance. So that is delta R, I can say. Okay. So that is what compression. Okay. And there will be a possibility you can have in a lateral forces and so many steps also you can measure. And this is bonded onto that particular surface. Just take an example. This is the bar. Okay. And I want to know how much deflection is happening at this location. Bonded means if I'm going to apply the force here, and this also should get moved. That's what it should be bonded, means it should be rigidly fixed to that particular surface. Then and then I can 100% accurately say my strain is accurately measured out here. Okay. So that is what happens in strain measurement. If it is not properly bounded, if I'm going to apply the force here and the strain is now slipping onto the surface, what will happen? Obviously, whatever the deformation happening in this particular delta will not completely reflect, but will have in a smaller values, and again it gives in a wrong values, and that's what this particular body and this particular strain gauge should be rigidly fixed to each other. Then and then I can get a complete information of change of the deflection to the change of the resistance. That is basically that's what bonding is the most important parameter into the strain gauges. Okay. Strain is an amount of deformation. So already we have said of the body due to the applied force. And specifically, it is in a fractional change in the length. Fractional change means it is a strain is represented with a delta upon L like this. Okay. Fractional change. The bonded gauge given to the strain gauge because it is glued so that it is rigidly fixed onto the surface. Okay. There will be a, you can just look at it. This is what it tells you how the force change the resistance take place. This is zero force applied. Force is zero. This is positive force, I can say. Means it is a tension it is going to generate. Okay, here you can see a change in the resistance meter. This is my zero, it is going to show. Here it is on a positive side, it is going to show me. And here it is going to show me a negative voltage. That is what it is going to tell me on a compression. Okay. So this is typically happens in terms of a strain gauge operation. There will be a different type of strain gauges like an resistive foil strain gauge. Okay. And in this resistance foil gauge, so it is a typically a foil type material. It is bonded into the small innate, and you can use that. And it is very small. It's like an our SIM card or size. Okay. So it is typically a low cost system. It is high response, speed, broad frequency bandwidth. Means it can take up in a large change in the frequency also. It is not like an our Wheatstone bridge or something. Then it can commercially available. It reduces. It's subject to electromagnetic noise. Electromagnetic means if I bring some magnet near to it, the signal generated or change in the resistance, whatever it is happening, it is going to affect it. And that's what we need to keep that electromagnet. Okay. And then interferences or offset is in that particular sensor. Long-term performance of the adhesives used for bonding strain gauge. Is again, uh, adhesive may get loosen out or may get damaged after certain period of time, and that is also going to affect your performance. Okay. Vibrating wire strain gauge cannot be used for the dynamic application because their low response speed, and that's what file type strain gauge will be used. And there is one more strain gauge is into the market that is costly affair, but it is used, that is optical fiber based. We'll discuss that in separately. Okay. So there will be an uniaxial strain gauge, okay, with a single grid. Okay, that is only one single axis. I'm going to use it. Then we can have a two perpendicular. It can sense both the direction. Okay, uniaxial means I can have an application of the force in only one axis. It will not sense the whatever it is happening in other direction. It will not sense at all, and that's what it is called as a uniaxial. In biaxial, then when we are going to embed two resistances, okay, two strain gauges into this, then it becomes in rosettes, okay. Then two perpendicular grids means one is sensing this direction, another this direction, and another is sensing this direction. That is what it can sense in x direction as well as y direction. It has no biaxis sensing, and these grades are kept into the perpendicular grades. Then there will be a three element strain gauges or rosettes. Three independent grids are connected one to like this. Then maybe in a kind of a membrane type, shear pattern, so many things you can have different arrangement for this. Okay. So there is a then there is the most important parameter in the strain gauge is its gauge length. How much length is that? So we can typically get 0.2 mm means it is 200 micron is minimum size, and 100 mm is my largest size. So that is the range. Minimum strain gauge length will be 200 micron to 100 means 200 micron I can give a feel of it, or hair diameter is typically 80 micron. I can keep this one or three hairs near to each other, and I can get a small strain gauge. This can be used for micro kind of sensing purposes, and this larger strain gauges will be mostly used in larger structures, civil structures, or maybe other mechanical structures. So this is a typical construction. This is the maybe on a file, wires, or anything. This is the loops, okay, multiple loops. This is the active gauge length because this is active gauge length. These are the grid lines. Then these are the solder tabs where you can connect your connection to your microcontroller. And this is what on a backing means it is going to hold this whole stuff onto this particular you know, metal, that is backing metal. There will be three different types. One is wire type. It is typically used, but it cannot be used for dynamic purpose mostly because this dynamic is changing with respect to time very fast. So it doesn't give any better results. But file type give me both good results in static as well as dynamic. Static as well as dynamic. It cannot be used for dynamic purpose, only used for static purpose. Okay. Helical coil wire is also used, and it is helically wound onto backing metal like this. Okay. So how to install that? So whenever you are going to install it onto any surface, so this is a typical surface on which you want to mount it. So you have to do it, you have to clean this surface so that there should not be any gap between your strain gauge and that particular surface. That's so basically reason for that purpose you need to clean it using different solutions like maybe an acid or kind of stuffs. Once we can neutralize any chemical reactions introduced in the conditioner by using neutralizer or something, and then you can apply you can even use emery paper or something to smoothen out that surface. And once we've done it, then you can apply a glue and paste onto this. Okay, this is a bonded type metallic strain gauge. Okay, there is one more factor mostly used in strain gauges is a gauge factor. Okay, so why it is called as a gauge factor, I will tell you. Because so what else input is going to then this is my strain gauge, I can say. This strain gauge is, I will consider everything in terms of a system. When we are doing in a mathematical model, you will come to know why I am doing it. Okay. So in strain gauge, what is the input going on? It is in a force is my input. What is output coming out? Strain, change in the resistance. That is what an delta R. I want to create in a relation between these two. Okay. Or I can say instead of force, I will consider as a deflection as an input to this. Okay. So I want to create relate these two parameters. Okay. So I can have total length is L here. Okay. And here original resistances are here and original length is here are here. Now, can I have an L? It is going to change L plus delta L, and here R is going to change R plus delta R. Maybe on a plus minus, I can say it is here. Means ultimately delta L is changing. Here it is delta R is changing. Can I convert that delta, what are the deflection it is happening into delta L upon L? This is my input and delta R upon my R. Okay. Then my transfer function or gauge factor, whichever the name you give it, is nothing but output divided by input, which is equal to output is delta R upon R divided by delta L upon L. This is going to give me basically conversion of the information from one type of information into another information, and that is what it is called as a gauge factor. Okay, so we can just look at this gauge factor is the same delta R upon R, delta L upon L, and this delta L upon L is nothing but our strain. Okay, that is the way this gauge factor relates to both those stuff. Okay, get the input and output. So once we know the change in the resistance, we can now measure that change in the resistance in terms of a change in the voltage. Okay, because microcontroller understand this voltage language. It doesn't understand change in the resistance, change in the length or something. It understands only voltage signals, and that's what I have to give him voltage signals. That is maybe that is what we need to convert it. To convert that change into the change in the resistance to the change in the voltage, there will be plenty of the circuits, like a divider circuit is there, then Wheatstone bridge is there, and so many other circuits. Even operational amplifiers are used and something. So to use this, mostly use Wheatstone bridge. Okay, why Wheatstone bridge is used? Because it is very much sensitive. Just take an example. If my resistance is 100 ohm and some change is 1 ohm or 2 ohm change, I want to sense it. This Wheatstone bridge gives me a better accuracy compared to any divider circuit. You can do a simple calculation. You can have 100 ohm resistance. This is 100 ohm. And I will now say having an apply 0 to 5 volt or something, I applied, and this resistance is now changed to 0.01 ohm. How much effect will have be there? Very small change you can observe it into the voltage output. Okay. But if I use this Wheatstone bridge, I can get a better accuracy, better change in the resistance conversion into the voltage, and that's what in 90% case Wheatstone bridge circuit is used in measuring this. What is that Wheatstone bridge circuit? Is typically measures the voltage output whenever it is going to change the resistance. In Wheatstone bridge, what it happens, we are using in a four resistances. This is R1, then R2, R3, and then R4. And one of the resistance is considered to be a strain gauge. If this R1 is equal to R2 is equal to R3 equal to whatever my gauge resistance are both all are equal, my output across this B and D point, okay, okay, will be zero all the time. Okay. If any of the change is going to happen in any of the resistance, voltage output will be same. It gives me some output. Okay. And that is typically in millivolt or something. And that is what a conversion happens, changing the resistance into the change in the voltage. And what of this circuit? You can do an electrical analysis, circuit analysis, and you will get this formula. Voltage output is equal to V in, what are the voltage supplies given here. Okay. And this is what in the formula you can get. This is a typically Wheatstone bridge kind of circuit. Okay. So this Wheatstone bridge is converts R1 that resistance, small resistance into voltage equal. Okay, this maintains this ratio R1 by R2, Rg by R3. If it is balanced, then it gives me 0 volt. Otherwise, it will give me some value. Will be positive, negative, depend on this ratio. Okay, and if my gauge factor already we have gone through it. Gauge factor is resistance change upon original change, then epsilon. Then I can have a strain gauge here. Gauge factor, strain gauge, and then I can get finally amount of strain I'm going to measure it. Okay. Then what are the output you are getting into an Wheatstone bridge, or it is a very low voltages. And again, in future, in further, we need to improve it or to a larger values. And that for that purpose, we use in a signal conditioning or kind of stuff. Okay, we'll take up on a few examples and okay, we'll have a typical. These are the slides I'm going to anyway share. So this is a typical strain gauge measuring unit consists test specimen, or here it is in a test specimen. Okay, this is my test specimen on which here it is in a strain gauge is mounted. It is very small. These wires are connected to the circuit. This is my entire what it is called, my Wheatstone bridge. This is Wheatstone bridge is built onto this, and this Wheatstone bridge is connected to your microcontroller. This is your microcontroller, and a microcontroller displays the output. Okay, and there is one more unit which converts that into higher values. That is what an amplifier. Hello. So here we can have a simple calculations how it does. Value read in the converted digital is available in one of the register of the microcontroller, and then ADC resolution is to be typically a 10-bit. Step size is 48.8 millivolt. Multiply 48 into actual analog voltage, divide voltage. These are the steps through which it will work out. Okay. So then later on you can determine, convert that voltage into strain using the gauge factor and kind of the stuff. Okay. So we can have a multiple such strain gauge measurement. We'll have finally one simple formula, and based on that we can get this. This is nothing but typically a voltage change or resistance change formula for measurement of strain gauges. Okay. There will be two types of compensations needed in the strain gauge. What is going to happen? In there will be two type. Why we need in a compensation? So in Wheatstone bridge, what it is expected that this R1, this R2, R3, and all this whole stuff, all should be equal. But what is this circuit is converted, mounted into certain box, and then strain gauge you are taking to somewhere else. Means you are connecting this point within a certain long wire to this strain gauge, and this point within a long wire to this strain gauge. So obviously, resistance in these wires will affect and will disturb your output, and that's what this type of a compensation is to be done, and that is what it's called as a wire type of compensation. And that's what here you can include wire resistance here in between wire compensation resistance is added into this. Okay, another one, there is a temperature compensation. You know that whenever we are going to change the temperature of any metal or something, the resistance of that particular material changes. Okay, resistance of that particular material changes, and that if I want to measure the displacement, and at that particular location temperature may be in a 50 degree, and my what are the box I'm going to use it having in a temperature maybe 25-30 degree or something. So this change in the temperatures of these registers, what are this one, two, three registers, and this register is different. Here your temperature is somewhere 30 degrees Celsius, and here it is in a 50 degrees Celsius. So obviously, this difference will affect the resistance into this particular gauge, and that is what it is to be compensated. And that's what they do it, they can take up an one more strain gauge out of it, and they will keep that strain gauge in that particular 50 degree Celsius. So what are the change in this particular loop, that is a downward loop, and this will be taken care into the upward loop also, because you are mounting one of the strain into that particular place, and that particular place is that gauge is called as an dummy gauge. It actually, this particular gauge will not be used for measurement of strain, but it is going to use to sense the temperature, whichever it is sensed by your strain gauge. And that's what this is what a temperature compensation circuit. And this can be further converted into strain rules. Itself is in a big topic, even strain gauge itself. It may take on a more than 5 to 6 hours of period to explain only strain gauge. But we are not mean to only work on the strain gauge, but we want to know how that strain gauge can be used in robotic sensors. Okay, there are different rosettes, like already we have seen the 2-axis gauge, 3-axis gauge. Then you can have membrane type, maybe a 45 degree stacked rosettes, 45 degree or 120 degree rosette or something. So there is one more sensor. It is called as a tactile sensor. And tactile sensor is tactile is the word which tells about touch or sense, that's what they use in a PVDF film. In PVDF, that is polyvinyl difluoroethyl, something. That is the material it is used. In this PVDF film, whenever you are putting in a pressure, okay, it is changing the resistance, and that change in the resistance will be sensed and is given to the amplifier, and amplifier will now generate a more signal, higher, means it converts into higher values, and it is mostly used in hands of robot, keyboards, or our keypads, which are we are using in our robotic systems or any other systems also. So here it is in fiber optic strain gauge. So change in the length. So fiber optic, how it works, I will tell you. This is my optical fiber. Okay. This is total, it is called as a total internal reflection, TIR. Okay. Total internal reflection. Based on this is what my, no, this is what a concept use. Reflection. Okay, so what is going to happen in optical fiber means it is what are the light entering into this is my light signal. Okay, maybe this light is used here, it is entering into one end, and this is going to reflect here onto this surface. This surface is completely reflective surface inside. It is created on entirely over cylindrically. It is this. So it is going to reflect 100% of intensity here. It's totally considered to be it is reflecting and it is traveling like this. Okay, that's what it is called as a total internal reflection. So when you are going to have such type of a fiber, okay, if I'm going to increase the length, it is if I'm going to send the signal light at time t equal to say 0 second, and it is reaching here with t is equal to 20 seconds, okay, and this length is L, maybe an 100 mm or something. Okay, it's very less second I'm taking, maybe microsecond or something, because it is light moves very high speed. Okay, if I change this length to L plus delta L by applying force or something, okay, I'm going to apply the force and it is going to increase the length of it. Obviously it has to travel more, this light has to travel more, and it is taking some maybe a 21 microsecond or something, and that is what a change in the time is converted into amount of deflection whatever it has happened, because it is directly related to amount of travel of the light, and that is what an optical strain gauge works out here. Okay. So whatever we are measuring into the strain gauges, it is due to the change in the temperature. It is going to affect a change in the temperature, low temperature coefficient of the resistance, and we need to have a temperature compensation circuits in so many places and kind of stuffs. Okay, there will be a bonding process. There will be there will be a thinning of the materials due to cycling. So many stuffs will be there. Okay. So I think I would like to stop it here.